Today we're going to do a deep dive into covalent bonds and molecular compounds, which are the types of compounds that form from covalent bonds. Okay, by the end of class today, you should be able to describe what's happening to the energy of the two atoms as their bonds form, and you should be able to draw Lewis dot diagrams for individual atoms and Lewis structures for molecules. Okay? All right, we'll just jump right in. So, molecules are neutral groups of atoms that are held together by covalent bonds. So if it is a molecule, then the atoms involved make it electrically neutral, so there's no charges going on. Maybe those partial charges we talked about, because polar covalent bonds are a thing, but the whole atom itself is not charged, okay? And they are held together by covalent bonds. If you're talking about a molecular compound, you're talking about a compound whose smallest unit is a molecule. I know this sounds a little redundant because I just said it, but this is going to be different than an ionic compound. So we're going to have different types of compounds. Compounds where you have different atoms, but a molecular compound is specifically a compound that's formed by covalent bonds and is neutral. So when I talk about a molecular compound, I'm talking about covalent bonds. When I talk about an ionic compound, it's going to be talking about ionic bonds, which we will discuss in the next section, that type of compound. Molecules can be made of two or more of the same atom. Okay, so a hydrogen and a hydrogen atom can share an electron, or they can be made of different atoms. An oxygen and two hydrogens can share atoms together. Okay. You can see what a compound is made of by looking at its chemical formula. Sometimes when we're talking about molecules, you will hear people call it a molecular formula. It's the same thing as a chemical formula. They're just being more specific to make sure you know that the formula they're going to describe to you is for a molecule, which means it will be covalently bonded and it will not have an overall charge. Formulas indicate the types and numbers of each atom that are in that compound. So, for example, with water, we have the symbol, the chemical symbol from the periodic table that tells us what atom is involved. So in this case, we can see hydrogen and oxygen being involved. And we have subscripts that tell us the number. So hydrogen, the capital H with the subscript of 2 indicates that there are 2 hydrogen atoms involved. Then we have oxygen, which doesn't have a subscript, which means that there is only 1 oxygen atom involved. Okay, having a subscript doesn't mean that there's 0 because the symbol is still there, which means that type of atom is there. Not having a subscript simply means that there's only 1 of that particular type of atom. And the subscripts can go higher than 2. Okay, there can be 3s and 4s and 5s and things like that. So it's just telling you type of atom and number of atom in that compound. Now, this may be not news to you. You may have seen chemical formulas before. I'm just doing a little refresher for you so that later when we get into the Lewis structures, this is familiar to you. Okay? All right, now let's talk bond formation and energy. We know, because we discussed it in the first lesson of this chapter, that sharing electrons allows atoms to lower their potential energy. As two atoms are approaching each other, they begin to interact, and there are several different forces that are at play during this interaction. The first force is the attraction between the positive nucleus of one atom and the negative electrons of the other. So if you had 2 hydrogen atoms, the nucleus of the first hydrogen atom would be attracted to the electrons of the second one, and the nucleus of the second atom would be attracted to the electrons of the first. So there is an attraction force there that causes those atoms to approach each other. However, we know that those opposite charges attract, but we also know that like charges repel. So those atoms are going to be experiencing some repulsion forces as well. There will be repulsion between the electrons of the first atom and the electrons of the second atom, and there will be repulsion between the nuclei of the two atoms. So nucleus of one hydrogen atom will repel the nucleus of the other. So you may ask yourself, how does this work? We have these attraction and repulsion forces. What does this really look like? How does a bond even form here? Well, the process is going to look something like this. If you were able to take two hydrogen atoms and separate them out far enough from each other that there was no interaction between them, and then you started to scooch them just close enough that they would sense each other, the first interaction that would happen would be the attraction force. Okay? It's going to be stronger at this point, and it's going to cause those two atoms to move towards each other. Then, as those two atoms get closer to each other, those repulsion forces are going to start getting stronger. And eventually, you'll find a balance between attraction and repulsion forces, and you will wind up with a stable bond that's formed, and potential energy will be at its lowest. A nice, convenient way to think about this is to think about it like rolling a ball down into a ditch. Let's say you had a nice little concrete ditch, okay, and you took a ball and you put it right here on the edge and you let it roll down in. Is it going to roll down and immediately stop here at the bottom? No. What's likely going to happen? Yeah, it's going to roll back and forth, right, until it eventually stops, okay? This is a good model for the way energy looks in these atoms, okay? So right here, at where I've labeled it 1, would be the point at which they just begin to attract each other, okay? So those attraction forces are really strong, and they pull it, okay? And then as they pull them closer and closer together, you're going to come over here, and those at the bottom, okay, this is our lowest potential energy. So it's low there, but then those atoms get attracted to each other, and then there's these repulsion forces over here at the number 2, where those repulsion forces come into play, and the energy rises again. And then they push it back, and then the attraction pulls it in, and then they push it back, and the attraction pulls it in, and eventually they settle right here at the low, where the energy is the lowest, and that's when you get a stable bond. Okay? And that's going to be a distance. There's going to be a distance between those two atoms. Okay? So at 1, that distance would be very far apart. They just begin to attract each other. At 2, that distance would be too close. The repulsion forces would be too strong for the bond to be stable. And so then at that L, at that lowest potential energy, that's where the stable bond forms. The distance between the atoms at that point where that stable bond is formed, we call the bond length. And that what that distance is going to be different depending on what atoms are involved. Okay? Because the strength of the attraction forces is different depending what atoms are involved. Okay? Because you're going to have some atoms that are more electronegative than others, and so they may pull on those electrons more strongly. Some atoms have a larger positive force in their nucleus than others. So overall, you're going to see lots of differences in bond lengths. When a bond is formed, energy is released. Because remember, we said they have a certain amount of potential energy before they connect, and then when they do connect, it lowers their potential energy. Well, that potential energy has to go somewhere, okay? It could be released as heat or light, but that potential energy has to go somewhere in order for their potential energy to be lower. However much energy they release is equal to the difference between their resting potential energy and the potential energy they have in the bond. whatever that difference is, that's how much energy they're going to release. And coincidentally, if you then want to break that bond to rearrange these atoms, you're going to have to put that much energy back in to break that bond. Just like bond length, how much energy you need to break a bond also depends on what atoms are involved. If you want to see some common bond energies, Figure 2.5 on page 178 of your textbook lists some common bonds that form between atoms and the energies associated with those bonds, but it's important for you to remember that those bond energies can be slightly different depending on what other bonds an atom has formed. So, for example, hydrogen and carbon form bonds pretty frequently. A bond between a hydrogen and a carbon atom is going to be different if that carbon atom is also bonded to an oxygen atom than if it's just bonded to a hydrogen atom. Or if it's just bonded to 4 hydrogen atoms, it will be different than if it's bonded to just 1 hydrogen atom. So knowing what other atoms are in there and involved is important, because all atoms are made up of charged particles, and anytime you put atoms with charged particles together in an area, they're going to influence each other. So if you just have a carbon and a hydrogen together, then those are the only forces involved. But as soon as you tack an oxygen onto that carbon, there's more forces involved. And oxygen's pretty electronegative, so it's going to have quite the effect on the bonds that you form. Okay, now let's talk about the octet rule. We've talked about this informally. Now we're going to formally write down what it is, okay? Atoms all follow the octet rule. Well, not all of them, but we'll talk about the exceptions. Most atoms follow the octet rule when bonding, okay? And that just means that it's most stable for them to have 8 electrons in their outer shell. We've discussed this before. We've said the noble gases on the periodic table, they all have 8 in their outer shell. That makes them really, really stable. So it's most stable for an atom to try and gain enough electrons to have 8 in its outer shell, or lose enough electrons that it would be a lower energy level and have 8 in its outer shell. In the terms of covalent bonding, which is what we're discussing today, they're only going to be gaining electrons, right? Because we're sharing so that nobody's losing anything. Example, fluorine atoms tend to bond with each other. This is because fluorine has 7 valence electrons. So if it can find another fluorine atom and they can each share an electron with each other, then they can have 8 total, because that shared electron counts for both of them. So they both get to count one of the other's electrons, and then they have 8, and that makes them extremely stable. As usual, there are some exceptions to the rule. The most common one that you'll see is hydrogen. Hydrogen atoms are in the first energy level, which means they only have an s orbital, which means the maximum number of electrons they can hold in their outer shell is 2. So it doesn't make sense for them to try and get 8, because then they'd have to move up energy levels, and that's difficult. So they, like helium, are in noble gas formation when they can have 2 electrons. So they will not form an octet. They will just try to get 1 additional electron, which means they form a lot of single bonds. Because, so this is just a written version of what I just said. Because their outermost energy level is full, that makes it a very stable configuration for them, even though they only have 2. The other exception we're going to talk about is boron. So boron has 3 valence electrons, and since in covalent bonds we share pairs of electrons, it can only form 3 bonds because it doesn't have a 4th valence electron to share, so it can't form a 4th bond, which means it tends to form stable bonds where it's only surrounded by 6 electrons instead of by 8, because it only has 3 to give. And lastly, and this is an exception that you won't see a ton, at least to begin with, maybe if you go on further in chemistry you might see some of it, but fluorine and oxygen and chlorine are very, very, very electronegative, which means that sometimes they can form bonds where they are surrounded by more than 8 electrons. But it doesn't happen a ton, at least not in stuff that we're going to study. These bonds that have more than 8 electrons surrounding them, these are the ones that involve the d orbital electrons that we talked about. Remember how we talked about atoms in the d block can sometimes involve their d orbital electrons in bonds? Well, it would be this type of bond. Now we're going to learn Lewis diagrams. Okay? Lewis diagrams are a method of simply drawing and representing atoms and how they bond with each other. So actual bonding between atoms is more complicated than this, and we're going to dig into it. But this is a really nice, simple way of representing the bonds between molecules formed when we want to draw them, like physically represent them. Okay? So, to begin with, we'll do Lewis dot diagrams. Lewis dot diagrams are just for individual atoms. So you don't draw a dot diagram for a molecule, you would only draw it for an atom. Okay? They are drawn by writing the element's chemical symbol first. Okay, so if you were drawing one for iron, you would write Fe. And then around that atom, you're going to draw dots that represent how many valence electrons they have, and you'll draw those dots in pairs of 2. There's a nice diagram on your notes already that shows you what that looks like. So I'm going to move forward to it, and then I can come back to this page if you still need it, okay? But the Lewis dot diagrams look like this. So the X is representing the chemical symbol, and then the dots show how many valence electrons. So if it only has 1, it's a dot to the right of the atom. If it has 2, then you put 1 above. 3, you put 1 on the left side. 4, you put 1 underneath. And then as you continue on to 5, 6, 7, and 8, you repeat the process in the same order, moving in the same direction, which is counterclockwise. Okay? All right. Now let's talk Lewis, or actually, I apparently put a practice in here for you first. So go ahead and draw the dot diagrams for hydrogen and nitrogen, and then we'll do them together in a moment. Okay, we'll start with hydrogen. What's the chemical symbol for hydrogen? H. So to draw our dot diagram, we'll write a capital H. Okay, and how many valence electrons does hydrogen have? Just 1, so we'll just put 1 little dot on the side. Okay, so that would be the Lewis dot diagram for hydrogen. Okay. What's the chemical symbol for nitrogen? N, so we'll draw ourselves a capital N. How many valence electrons does nitrogen have? Well, because it's in the P block, we can take its group number minus 10, which is 5. 5 valence electrons. It's in group 15. If we subtract 10 from that, we get 5 valence electrons. So we can go ahead and fill in 1, 2, 3. It's a bad one. Try that again. 3, 4, and 5. So that is what the dot diagram for nitrogen would look like. Okay. That's dot diagrams. Now let's talk Lewis structures. Lewis structures are used to represent atoms that have bonded with each other. So in this case, we're drawing molecules. The chemical symbols of the elements are still used to represent them, so that part doesn't change. And we still represent electrons with dots. If you have an unbonded pair of electrons, or what we call a lone pair, then we use 2 little dots right next to the atom. If you're representing a bond or dots shared by atoms, then you're going to draw them between the atoms, or in order to simplify things and not have too many dots on the screen, you can change them into a line. So for example, if I was going to draw carbon, bonded to some hydrogens, I could either draw 2 dots between the two, or between each hydrogen and carbon, which would look like this, and it's fine, but it is a little bit messy. So instead, a lot of people prefer to draw a line to represent your bond. So each bond represents a shared pair of electrons, which means it's 2 electrons and they can be shared by both atoms. So hydrogen can be considered to be having 2 electrons right now, and carbon can be considered to be having 8 because it's sharing 2 with each of the surrounding carbons. Some atoms form multiple bonds. Okay, they might form a double or a triple bond. For example, nitrogen atoms each have 5 valence electrons, which means that they will often share 3 pairs of electrons with each other to reach their octet. If you are drawing this, then each additional bond is represented with either an extra pair of dots or an additional line. So what that might look like, and I'll come back to this, so don't panic, is if you had nitrogen, okay, we know nitrogen is going to share 3 pairs of electrons. So you can either draw 3 pairs of electrons between the 2 atoms, like this, to represent that triple bond, or you could simply draw 3 horizontal lines to represent your triple bond. And then they each have their own lone pair, which brings their total up to 8 shared electrons each. All right, let's talk through the steps for drawing a Lewis diagram, and then we will try them, okay? So step number 1, determine the type and number of atoms in the molecule. Step 2, write the electron dot notation for each type of atom. So if you have, 3 carbons, a hydrogen, and an oxygen, then you would draw the Lewis structure for carbon, for hydrogen, and for oxygen. Then determine the total number of valence electrons available in the atom to be combined. So you're going to total it up. If you have 3 carbons, each carbon has 4 valence electrons. So that's 12. Then you have an oxygen. Oxygen has 6 valence electrons. Okay, so now we're up to 18, sorry. And then if you have 2 hydrogens, then they each have 1. So now you're up to 20. Okay, 20 valence electrons. Then you're going to arrange the atoms to form a skeleton structure. So you're just going to place the atoms, the symbols for the atoms around each other so that carbon is in the middle if there is a carbon, or if there is not a carbon, the least electronegative atom is in the middle, obviously excluding hydrogen because hydrogen can only form 1 bond, so it's never going to be in the middle of a molecule. Okay, whatever atom is in the middle needs to be able to form a lot of bonds. That's why carbon goes in the middle a lot. Then you're going to connect the atoms by their electron pair bonds. Okay, to begin with, we will assume single bonds. We'll come back and fix it later if it's not. Then add unshared pairs of electrons to each of the nonmetal atoms except for hydrogen so that each of them is surrounded by 8 electrons. So if I have a carbon atom and it's only forming 3 bonds, then I'm going to give it a lone pair so that it has 8. Because each of those 3 bonds represents 2 electrons, so it would have 6. So I'm going to give it a lone pair so it has 8. Okay? And after I do that for all of my atoms, obviously except hydrogen, because hydrogen will only form, it won't have a lone pair because it's only going to form 1 bond because it only needs 2 electrons. Okay? Then I'm going to count how many electrons are in my structure to make sure the number of valence electrons equals the number I said I should have at the beginning. And then if they all have 8 and that number is not correct, if I have not enough, I will go back in and make sure everything has 8. If I have too many, then I need to check and see where a multiple bond is going to form, because that's how I'm going to eliminate some. All right, we're going to try this now, okay? So On practice number 1, they want you to draw the Lewis structure for iodomethane. Somebody who has the steps still showing on their paper, what's step number 1? Identify the type and number of atoms in the molecule. Okay, so I have 1 carbon, right? I always forget to switch over to drawing mode. I have 1 carbon, and I have 3 hydrogens, right? And I have 1 iodine atom. Okay, now you don't always have to draw them all out like this, but because we have so few, I'm just doing it. Okay, what's next step?
Write the electron dot notation for each type of atom.
Okay, so I need to do electron dot notation. How many valence electrons does carbon have? 4. So I'm going to go ahead and draw those around him. How many does hydrogen have? 1. So I'm going to go bink, bink, bink. And then how many does iodine have? 7. So 1, 2, 3, 4, 5, 6, 7. All right, there's my dot diagrams. How many total valence electrons do I have there if I add them up? 14. That's going to be important later. Okay, now I want to arrange them in a basic structure. Which of these is going in the middle? Carbon, because if you look at the rules, it says if carbon's there, carbon always goes in the middle. So then we're going to put iodine and hydrogen around carbon. Okay, this basic like square structure like this is pretty common as a way of drawing this. Okay, now we're going to do what? What's next? We've drawn our basic structure. Yeah, we're adding in a single bond for each of these, okay? We're starting off assuming a single bond, okay? And then what do we need to do?
Add unshaped pairs of electrons to each element.
Okay, so here's where we're checking for the octet rule and adding in lone pairs of electrons to get everybody to 8, except for hydrogen. Okay, hydrogen needs to have 2. So each bond counts for 2, and it counts for 2 electrons for each atom that it's connected to, because remember, they are sharing these. So if we look at hydrogen, this hydrogen has 2. Okay, this hydrogen has 2 in that bond, and this hydrogen has 2 in that bond. So the hydrogens are happy. They have 2. Then we go to the carbon atom. We count 2, 4, 6, and 8. Does carbon have 8? Yes, so carbon is happy. Carbon does not need any lone pairs. Then we're going to come up to iodine. How many does iodine have? It just has 2 in the drawing that we're showing right now, which means we need to draw in some lone pairs. How many pairs to get it to 8? 3. So we're going to go 1, 2, 3, 4, 5, 6. And there is our 3. So if we count, now we have 1, 2, 3, 4, 5, 6, 7, 8. And iodine has 8. Okay? Now, last step, we need to double check that we have the correct number of valence electrons. So we're just going to count all of the lone pairs and all of the bonds. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Is that how many we said we should have? Then this diagram is done. This is accurate. It has the 14 valence electrons that we said it should have. All right. Let's try one more. This time, we have carbon, hydrogen, and oxygen. I'm going to go ahead and draw in the carbon and hydrogen. How many valence electrons does oxygen have? 6. Okay, so now which atom's going, how many total valence electrons? 12 valence electrons. Which atom's going in the middle of our structure? C, carbon, yes. And then we're going to put an H, and an O in. And we're going to connect them with our lovely little single bonds. Okay, now we can go in and count here. This hydrogen has 2, it's happy. This hydrogen has 2, it's happy. Carbon has 2, 4, 6. So what does carbon need to get to 8? 2. So we're going to give it a nice little lone pair here. Okay, oxygen has 2. How many does it need to get to 8? 6. So we'll go and add in 3 pairs of electrons. Now we're going to count up total electrons. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Is that how many we said we should have? No, we have 2 too many. So what we're going to do is we need to take one of these pairs and we need to make it another bond instead. Okay? Because we have 2 electrons too many. Which atoms are going to do the sharing of this extra pair? C and O, because the hydrogens can't, right? So what we're going to do is we're going to erase these guys off of both of them and instead make it a double bond. So now when we go through and count, carbon has 1, 2, 3, 4, 5, 6, 7, 8. And oxygen has 1, 2, 3, 4, 5, 6, 7, 8. Everybody has what they want, and we have our correct Lewis structure with 12 valence electrons. That's where we'll stop. We'll pick up again tomorrow.